So welcome all to the last week's tutorial on essential mathematics for machine learning. I'm Pintu Kumar. I'm a PhD scholar at IUR IIT Bombay. The topic that I intend to cover today is related to support vector machine. I'll talk about linear separability in the beginning, and then we'll go to support vector machine, its motivation and its sort of derivation. Then we'll talk a little bit about duality. So that we are able to derive the dual form of the optimization problem that we encounter in support vector machine. And this is an overall agenda for today. So during the tutorial, at any time, if you have any doubt, you can unmute yourself or you can type it in the chat box. I'm looking at both of them. So yeah, I'll begin. So whatever we are covering today is related to classification. Okay, so I hope all of you are aware of what is a classification. So in classification, it is a supervised machine learning technique. So your data set would look something like x comma yi, where your xi is your feature and yi is associated label. Okay, and yeah. So this is classification. So you will have some training data set based on which you will come up with some hypothesis, which you will use to which you will later use to classify your testing data set. Okay. So the concept of linear separability generally we encounter for binary classification data set. So your yi's can take only two values. Let's say we call it 0 and 1. Or we can call it -1 plus 1. That would be useful for SVM derivation. Okay. So let's say we have only two labels, then we encounter something known as linear separability. Okay. So what is linear separability? So let's begin with an example in 2-dimension. So let's say you have a 2-dimensional plane. That means your feature vectors are 2-dimensional. Okay. So your xi's that you are, those belong to R2. And you have, let's say, two type of data set. Let's say this is +1 kind of data set, and let's say this is -1 kind of data set. You can see that if I draw a line over here, on one side I have only +1 type of data points, and on other side I have only -1 type of data points. So this kind of data sets, which can be separated into two halves by a straight line, are known as linearly separable data set. Okay. Okay. Now, next important thing is, so how does a equation of a line looks in 2-dimension? Let's say this hypothesis line looks something like this. Is not the exact equation of this line. I'm just taking some random line. So a general equation would look something like this, right? If we want to write it more cleanly, we can write it as, let's say 2. I can write it as 2, 3 times xy is equal to 4. Okay. Which is, if I call this thing as W transpose, if I call it as, let's say, X, capital X, and this is B, then equation of a line is given by W transpose X minus B is equal to 0. Okay, in 2-dimension. And an important property of line is, so if you look at the perpendicular vector to your line, this vector is nothing but your vector W. Okay. And another thing is, let's say, if you take any point over here, if this is your direction of vector W, if you take any point on the right hand side of your line and you calculate, let's say that point is X star, and you calculate W transpose X star minus B, then the value that you will get would be strictly greater than 0. Okay, this is the property of any line or a hyperplane. Okay. And if you calculate its value on any point over here, let's say this is x minus, then your W transpose x minus B would be strictly less than 0. So your line divides your complete R2 plane into two partitions. On one side, if you will put the value of x star in your line, equation of your line, you will get value greater than 0. On the other half, you will get value less than 0. Okay. So this is the property of your line. Okay. Now let's try to generalize this notion of linear separability, because your data point might exist in very high dimensions. So let's say you have data sets like this, and your xi belong to Rn. Okay. So then how does a separating hyperplane look? So this line is something known as separating hyperplane. Okay. So what was the equation for this separating hyperplane? This was W transpose x minus B is equal to 0. The same definitions holds here, but now your W vector belongs to Rn, because here also your W vector belongs to R2. Now your W vector belongs to Rn, and this line that you will obtain is an n minus 1 dimensional hyperplane. Okay. So in 2 dimension you got a 1 dimensional line to separate. So in 3 dimension you will get a 2 dimensional plane to separate. Similarly, if your data set belongs to Rn, you will get an n minus 1 dimensional hyperspace. Okay. So that will separate your data points. Okay. So this is equation of your hyperplane. Okay. Now let's say you have some data set D. Okay. Now we will call it linearly separable if there exists W belonging to Rn and B belonging to R such that W transpose X I minus B is greater than equal to 0 whenever your Yi is equal to 1, and this W transpose Xi minus B is less than equal to 0 whenever your Yi is minus 1. So in higher dimension also it is able to differentiate between these 2 points based on your value of W transpose X minus B. Okay. Any doubts in this? Yeah, any doubts in whatever we talked about linear separability, why we take W transpose X minus B greater than equal to 0, or those things? Okay.
Sir, can you explain the term hyperspace which
Sorry,
you just
I
said?
meant hyperplane. Okay, so what is hyperplane? I'll explain it to you. So in when you draw something like W transpose X, so if you draw something like 2x plus 3y is equal to 4, let's say, in 2 dimension it is a line. Okay. So, but if you exceed its dimension, let's say this is 3y plus 4z is equal to 2, then this is the equation of a plane, right? You call it a plane in 3 dimension. So if you take it to higher dimension, there is no special name for something of 3 dimension. There is no different name for something of 4 dimension. We call all this all together to be hyperplane. Okay. So plane from here, and you use a word hyper in front of it. So if you have something like 2x plus 3y plus 4z plus 1a is equal to 5. So a higher dimensional generalization of a plane is something that is known as hyperplane. Was I clear?
Yes, sir.
Okay. Okay. So now, like in the beginning of this course, we learned about logistic regression. Okay. And like if some of you have done some course on machine learning, you might be aware of other classification techniques like decision tree, okay, or random forest, or those kind of things. Now, why do we want to learn about SVM as such? Okay, so let me draw two lines. Okay, one line is this line, this black one. Okay, and another line is this orange line that I'm gonna draw. Let me just shift this a bit. Yeah. So which of these two lines do you think is a better classifier for this data set I have drawn? So these are two classes of data sets. One is green and one is purple. So which line among this black one and the orange one do you think is a better classifier? So yeah, the orange line is a better classifier because let's say uh, a point belongs here, right? The black line would predict it to be belonging to the green class, but this is pretty close to the purple class, right? So the confidence with which I am predicting this to be green class is very low. Okay. So if I have points closer to my this separating hyperplane, the confidence that I have in prediction in black line's case is pretty low. Okay. Whereas if you look at the orange line, this is sort of equally spaced from the green data set as well as the orange data set. Okay. So the idea behind SVM is that you want to maximize these two distances, some of these two distances. So let's say this is D L dash. So you want to find such a separating hyperplane so that your this distance is maximized. Okay. So this is the motivation behind SVM. Now I'm going to sort of try to derive this SVM thing. Okay. So before that, I would like you to recall one theorem that was done in the course, I think last week, which said that let's say if you have a data set, right, again, and if you have, let's say A plus denotes the matrix containing all the positive class data set, A minus denotes all the data points containing negative data set, and if you have something like A transposed A this multiplied by W minus B, yeah, I think no, yeah, if this thing is let's say greater than equal to B, okay, and A minus W is less than equal to B, then you can suitably scale your W so that you obtain something like this was E also over here. So you can suitably scale it to A plus some new W star, which is greater than BE plus E. Okay. And similarly over here. Right. So what does this mean is that now in the definition of linearly separable, we said that, so let's say if some point W transpose X minus B is strictly greater than 0. Okay. So that means if you want to replace this inequality with, let's say, less than equal to, you can replace this 0 by some very small, some positive quantity, right? So that positive quantity would vary from your X to X, your data point to data point. But let's say you can replace it by some epsilon I. Okay. So this W transpose X minus B is greater than equal to some epsilon times I, epsilon I. Then you can scale your WB so that this epsilon I becomes 1. Okay. This is the basic idea. Okay. So now for SVM, what we want is rather than W transpose X minus B greater than equal to 0, if we will classify these points to be of +1 type, and for points which satisfies less than equal to 0, we classify them to be of -1 type. What we want is, rather than having 0 over here, we want 1 to be here. Okay. And we can scale it. We had a theorem saying that we can scale it in such a way. Okay. So this is one thing. Now, let's say you have two types of data points. Let's say this is the purple one. Oh, sorry, this is the orange. And you have some green data points. Okay. Now, if you talk about the distance of any cluster or type of data points from this separating hyperplane, so you talk about the distance of nearest point from the separating hyperplane. So you don't take distance from all the data points, but you take the distance only from the nearest point, right? And you want to maximize this distance. Okay. So before we maximize this distance, let's look what this particular distance is. Okay. So let's say this point is my x tilde. Okay. From which I am drawing a perpendicular to this point x plus, which is my nearest positive point to my separating hyperplane. Okay. And now let's say this is some origin. Then this vector is nothing but your x tilde vector. This vector is x plus vector. And we want to find this gamma, right? So now this vector, let's call it gamma vector. Okay. And its length is also length of this gamma vector is gamma, let's say. Okay. Then by you can see that these two are vectors. By parallelogram law of summing of vectors, we can say that this x plus is nothing but my x tilde vector, right? Plus, now what is this vector gamma? Now this is gamma vector. What is this gamma vector? So as I mentioned few minutes ago, the vector in the direction perpendicular to your line is nothing but your W vector. So if this is W transpose X minus B is equal to 0, then this vector is your W vector. Now what is the magnitude of this vector? So the direction is this W vector divided by norm of W, and the magnitude would be the gamma, the length of this, right? So we can replace it by this, that is gamma times W by norm W. Now this is minus gamma vector, right? And this is your let's say x minus. So we can obtain a similar thing from here also, that is x tilde minus gamma, right? W by, okay. So let's call this equation 1. Let's call this equation 2, right? So if we now take the difference of these two equations, what we can obtain is that x plus minus x minus, these two are vectors, is nothing but 2 times gamma W by W, right? So now what we can do is, okay. Now another thing that I want to mention over here is, so whichever, now I impose an extra condition that W transpose X minus B should be greater than equal to 1, but the points, these points which are closest to your separating hyperplane, these points are also known as support vectors. And from here only we get the name support vector machine. Okay. Because even if you remove all other points from your data set and you just keep these support vectors, you will get the same separating hyperplane. So because this method is just based on these points, the closest points, that's why this method is known as support vector machine. Now mathematically, these support vectors satisfies a property, that is, so I said that all the points on this side should be greater than equal to 1. But for support vectors, this value must be exactly equal to 1. Okay. And similarly for these points also, that W transpose X minus B should be exactly equal to 1. Okay. This should be minus 1. Okay. So yeah, this should be minus 1. I'm really sorry for that. Now, because this X plus point satisfies this property that my W transpose X plus minus B should be equal to 1. If I replace the value of X plus from here, what will I obtain is, I'll obtain that W transpose 2 gamma W by uh, uh, W, right, plus X minus B is equal to 1, right? Or this is equivalent to 2 gamma W transpose W, right, by norm W, and this is plus W transpose X minus B is equal to 1, right? Now, this value I said is again minus 1, right? So, this implies this value would be minus 1. So, from here we can derive our gamma, right, which is nothing but this would be 2 gamma, and this is W transpose W, so this is norm of W square divided by norm of W, okay, and this would be nothing but minus 1, it should be, this should be 2, right? So you obtain your gamma to be 1 upon norm of W. Okay. So this is the distance on one side. This is the value of distance on one side, that is norm of 1 upon norm of gamma. You will get the same distance from the other side also. So the total length of this margin is so total length of margin is 2 upon norm of W. So what was the motivation behind this support vector machine? That we want to, okay, I'll get to that point, whoever has raised. So yeah, so our main goal was to maximize this distance. So the task of support vector machine can be summarized as a optimization problem, which is I want to maximize this thing and I have some constraints. What are those constraints? Those constraints are these two constraints. Okay. So, okay, so for so W transpose X minus B should be greater than equal to 1 if my Yi is 1 and W transpose Xi minus B should be less than equal to minus 1 if my Yi is equal to minus 1. I can rewrite this thing as So maximizing 1 upon A is same as minimizing the reciprocal of it. Okay. And I'll club these two constraints. So this can be written collectively as yi into W transpose xi minus B is greater than equal to 1. So my task of SVM is reduced to minimizing this quantity. Okay. And subject to these constraints. So this is something about SVM. Now somebody asked some question in between. The question is, please describe how W is perpendicular to. I didn't got your point, Vijayni. What did you wanted to ask? How is this line perpendicular to uh, this particular hyperplane? Is this, yeah?
Hello.
Hello.
Good evening, sir. Sir, here W is a point like A1 and A2. Then what is the meaning of that is a perpendicular? Because we get
Okay.
only a point, so then will.
Okay. W is not a point. W is your parameters for your support vector machine. Okay. So I'll motivate this answer by this example. So here you had a line that was separating these two hyperplanes, right? Then W was the coefficient of your line. So if your line is something like 2x plus 3y is equal to 4, then your W is your vector 2, 3. Okay, which is the coefficients of your hyperplane that you have learned or you want to learn. Okay, so W is not a point. W is the coefficient of your hyperplane or the hyperplane itself, you can call it. Okay, that's why we are talking about the perpendicular, right? Am I clear?
So when we say that 2 or 3 is a vector, it means we join the point 2, 3 and the origin, and then we will
Yes,
get a vector.
yes.
We will say this vector, but in this as you told that W is perpendicular to the line.
Mm-hmm.
Then what is the meaning of this vector?
Okay, so
When we draw when we draw W on the line,
mm-hmm. So
then
what
it
we
is.
mean, what I meant was the direction in which I'm moving. So let's say you have, let's say this is point 1 comma 1. Okay. So if you draw a line, this vector has two things, right? It has some magnitude and it has some angle or the direction associated with it. Okay. So when I say that if I draw a line perpendicular to this thing and that perpendicular line is my W, that means the angle at which this line is drawn is same as if I would have drawn 2, 3 starting from the origin. Okay. So this means the angle is same as the vector 2, 3. Okay. I was not clear. Okay. So let's say this is your, okay, let me draw a fresh one. Okay. So if you want to draw, let's say, some perpendicular at this point to this line, so that would look something like this. Okay. Now, if you want to represent this vector or this whatever we have drawn over here, this is a direction. If you terminate it, then it will have some length also. So if you want to represent this, how would you represent? Okay, so it will have two things. One is its angle and one its length, right? Now if you just pick this line from here and you placed it at origin, it's one of its end at the origin, then you would have got the same thing, that is your 2 comma 3. Okay, so that means the angle that we are having, if we start from here, it's same as if we would have just lifted it and placed it at the origin. This is what it is meant that W is perpendicular to this. Now am I clear?
Yes, sir. Now it is clear. Thank you, sir.
Okay. Any other doubt in the derivation of the support vector machine that we just did? So why do we sort of minimize this quantity, that is 1 upon 2 norm of W? That I think should be clear. If it is not, please ask.
So in beginning, you took an example of A plus W greater than BE and
Yeah,
less than BE.
yeah.
Sir, can you explain that? You said that it has been done in previous class, but I don't think it was taken.
Yeah.
Possibly.
I didn't did it, but I think in the lecture it was done. So you are talking about, I would come to that point. This one.
Yes, sir, this one.
Okay. So I won't go into the proof details, but I'll try to intuitively tell what is happening over here. Okay. So let's say you have A1 x1 plus B1 x1 strictly greater than 0. Okay. So you have strict greater than equal to 0 over here. Okay. Now you want to change this thing to greater than equal to. Okay. So one choice that you have is that B1 x1 is greater than equal to 0. This is correct, right? But because this thing is strictly greater than 0, right? And your data point that you have, that is also finite. Okay. So you can look at all the values that you obtain from A1 x1 or B plus B1 x2. Okay. And you can come up with some, let's say, value epsilon, so that, and this epsilon is strictly greater than 0, that your A1 x1 plus B1 x2 is greater than equal to this epsilon. For example, let's say you can get something like B1 x2 is greater than equal to 0.2. Okay. So is this step clear, that if you replace this strictly greater than equal to 0 by this epsilon, then you can get some greater than equal to epsilon. Is this thing clear? Kushal,
Sir,
yeah.
no,
No, it is not clear. Okay.
no, it is not clear, sir. I think
Okay.
we do a similar kind of thing in series conversion and divergence derivation also.
But in series
Absolute.
thing, you have infinite, right, infinite terms. Here we are just dealing with finite, so we can take minimum, and those kind of things are well defined. Okay, I'll draw something, then I think it will be definitely clear. Okay, so let's say these are two sets. Okay, now this is a finite collection of points that you have, right? And let's say you drew this as your separating hyperplane. Okay. Now, one thing that I told you, let me erase this thing and draw a proper line that I use. Okay. Okay. So this line gives you W transpose X minus B is equal to 0. Okay. This particular line has this equation. Okay. And these points on the right side have W transpose X minus B strictly greater than 0, because none of the point is lying on this line. Everything is on the right side of this line. Okay. So if you want to see this particular point, for example, okay, this particular point, and you want to see what kind of value does this satisfy. So if you just shift this line by, let's say, some epsilon distance, then you will get this line. Okay. Okay. So now if you have shifted this by epsilon distance, what would be the sort of equation for this line? That W transpose x minus b is something related to epsilon. Okay. So this point is satisfying W transpose x minus b is equal to epsilon, which is strictly greater than 0. Okay. Similarly, other points will also have, let's say this is epsilon 1, then someone will have epsilon 2, and so on, right? Now, if you take minimum of these epsilons, so let's say my epsilon star is minimum of epsilon 1, epsilon 2, and so on till epsilon n. Because this is finite set, we have this minimum well defined. Okay. So we can say that for all these data points, we have A1x, sorry, this is W transpose x minus B is greater than equal to this epsilon star. Okay, we can say this, right? Can we say this?
Yes, sir.
Yeah. So that is what I told you, right? Now, if we suitably scale this W and B, okay, so let's say you take your W to be this length of epsilon uh, times your you can take it as length of epsilon times you take a new W, which is your W star, as W into epsilon time. Wait, just give me a second. You take your new W as, let's say, old W divided by length of epsilon star, and you take your new B also as B by, let's say, epsilon star. Now, if you change your W and B in such a way, then what you will get? So what I'm going to do is I'm going to replace W transpose and B over here with their new values. Okay. So what I get, this is epsilon star W star this complete transpose x minus B star into epsilon star. This is greater than equal to epsilon star. Okay. Now I can take epsilon star from everywhere common and cancel it out. So I'll get W star transpose x minus B star is greater than equal to 1. Okay. So this is what I said, that if you have strict inequality, that is some W satisfies W transpose x minus B is greater than equal to 0 for some finite set, then we can replace this thing by this quantity. Now this W star and W are not same, but these are some scaling and this is a new W star and B star that we got, but we can find such W star and B star which satisfies this property now. Now am I clear? And similarly, you can do for this part also and take the minimum combined. Okay.
Yes, sir. It is clear.
Okay. Thank you. Okay. So anybody else has any doubt related to how we reach to the point that finding the maximum separating hyperplane is nothing but minimizing this particular thing, that is 1 by 2 norm of W subject to these constraints. Okay, this is for all I. So I over here denotes the data point. Yeah.
Sir,
Yes.
please explain the thing which is rounded by yellow color. How we got yi multiplied.
Okay. So till this point, was this clear that we got two constraints? So I just explained that. So everything on the right was satisfying this thing, right? So we replace this by this, And similarly for the negative points, we replace this by less than equal to -1. Till this point it was clear?
Yes, sir.
Okay. Now we did nothing. So if you look at it, whatever I have written, now this thing is greater than equal to 1, right? Now if I multiply it with yi, that is +1, so what will I get? Let's say if I multiply it by yi, w transpose xi minus b, this is also greater than equal to 1, right? And this is 1. So the product will be greater than equal to 1. Okay. Now if we look at the second part, so for the second part, this thing is less than equal to -1. Okay. And this thing is -1. So if I multiply these two things together, so minus multiplied by minus would become +1. And because I'm multiplying negative things together, the sign of this inequality changes and it becomes greater than equal to, right? So if I just multiply this thing by yi, I can combine these two constraints as a single constraint. That is, my yi multiplied by w transpose xi minus b is greater than equal to 1. Was I clear?
Yes, sir.
Okay, thank you. Okay. Yeah. Okay. So if your data point, whatever we discussed, if these data points, as you know that they were linearly separable, we assume them to be linearly separable. So the kind of this classifier that you obtain over here is known as hard margin classifier. Okay. Or hard margin SVM you can say, or hard margin classifier. What does this mean is that on one side of my separating hyperplane, I have only one type of data points. Okay. But when you look at some real world data set, it's very, very rare that you will get some separated data point. That is, some data points is linearly separable. Okay. Generally, it will happen that the data points are not linearly separable. Okay. So, for example, so let's say these are my plus points and these are my minus points, and there is some plus point here or there is some minus point here. Now, how can we separate these? Right? So it is not linearly separable, right? So whatever linear classifier we draw, there will be some one or the other some training error, right? Okay. So what we do to tackle these kind of situation is we allow some error in the classifier. Okay. So earlier what we were assuming is that yi w transpose x plus this can be minus or plus, then the sign of b would change. Okay, is greater than equal to 1. This is what we were assuming. Okay. Now if we restrict r, we allow this error to be crept into it. So now for this point, I should have yi w transpose x minus b. This thing I should have less than equal to -1, right? For this shaded point. Okay. But this is on right hand side of my classifier. So what I did is I allowed some error xi into it. So if my xi, let's say, take some values greater than equal to 2, and these xi's are strictly greater than equal to 0. So let's say my xi take value 2 for this particular data point, then this property is also satisfied. Okay. So I allow some error in my constraints. Okay. So now the new set of constraints become, so for the time being, just forget this thing. I'll come to this thing. Okay. So just compare it to the previous case. We have minimize W transpose W, that is norm of W. Okay. If you square it or don't square it, doesn't make a lot of difference. Okay. So minimize 1 by 2 W transpose W. If you square it, becomes a bit smooth, and you can optimize it more nicely, but the optimum points that you will get will be the same. Okay. Subject to these constraints, that my Y transpose W yi into W transpose X plus B or minus B, that is up to you, you can change your notations, is greater than equal to 1 minus epsilon. Okay. Now, if I'm allowing the error, I don't want that my hyperplane that I get is something like this, the orange line that I drew towards the end. It should be in between, right? So what should we do is that these errors that we are introducing, okay, so this should be as small as possible. Okay. So to incorporate that term, we include summation of xi I in the minimization term along with a hyperparameter C. Okay. So if the value of C you take it to be large, right, that means it will allow very less error in this thing. Okay. So it will be, so let's say if this data point was not here, then I would have tried to minimize this error if the value of C is very large, and I would have got something like this green hyperplane. Okay, because I want my margin to be maximized, but at the same time I'm also wanting this error to be reduced, and I'm weighing reduction in error more than my margin thing. Okay, but if my C was less, for example, then I would have got some nearly perfect SVM kind of margin. Okay, so that depends on your sort of application. You can tune this value of C. Okay. And this kind of whatever classifier you'll obtain from here, those are known as soft margin classifier or soft margin SVM. That means your classifier is a bit soft in its decision, that it can allow some error also. Okay. Okay. Any doubt in this?
Sir, please repeat the concept of adding xi I
Okay.
and please explain in the figure.
Okay. So okay. So if you had this kind of data set, okay, the data set that I have drawn right now, you can easily separate by a hyperplane, right? So for these data sets, you would have W transpose X minus B is greater than equal to 1. You can find such line. And for these, you should have W transpose X less than equal to minus B, yeah, right? So you can find such line, okay. Now, let's say there is one more data point that is over here, okay. Now, what do? Okay, because any line you choose, you won't be able to find a line which satisfies this property, because this green is in between these orange lines. Okay, so because this is not linearly separable, so you can't find a line for which on one side you have orange points, on one side you have these points. Okay, so what we do is, for this green point, we want this green point to be sort of here, right? We want this point to be here. So for this point, what is the value of W transpose X minus B that we should get? This should be less than -1. Okay. So for this point, how can we reach from 1 to -1? We can subtract some positive values. So this xi I that we have is greater than 0. So now how much to subtract, that will be done during optimization. Okay. What we want is, we want to subtract some value so that this becomes similar to this. Okay. And we multiply it by yi also. Okay. Yeah. So this is the concept that we wanted to do. Okay. Am I clear now why I did subtract minus xi from here?
Yes, sir.
Okay, thank you. Okay. Okay, so it is 6:56 right now. The next topic that we'll cover is related to this duality thing. So this is my primal uh, optimization problem that I get. We'll try to convert a hard margin SVM to its dual form and see how it is done, right? And then why I'm doing it. So in the last two sessions, which are your Python based session, what I saw was that kernel functions were discussed, right? But I didn't saw kernel being discussed during the lecture. So I'll try to devote some time towards the kernel. But to understand kernel, you need to understand this particular formulation, right? Over here, there is something that you need to know. So let's take a break of 2 to 3 minutes. We can meet again at 7:01. Okay. So then we'll continue our discussion on support vector machine.
Sir,
Yes. Yes.
sir, can you scroll up to that page where you explained me about the topic of, I asked a doubt earlier. I need to write something.
Okay. So where?
Yes, sir, here.
Okay. Most probably no, Abhinav. This might be the last session, but like if you guys post some questions on the discussion forum, and if we feel that there is a need of one more session, then it will be announced on the discussion forum only. Otherwise, this would be the last session, last tutorial session. Because generally, not a lot of people ask question in these sessions also. So I'm not sure if there would be sufficient number of questions being asked there. So that's why we are not having one. Okay, Abhinav, we'll try to. Okay, we'll try to look at the question. If you have doubt in it, towards the end of this session only. Okay, so yeah. Okay. So now we will have two, three things going on here. Okay. So I'll tell you what will happen. So we got to a primal formulation, okay, of our optimization problem. I'll change the pen color. Okay. Now, using Lagrange, we will convert it to its dual form. Okay. And then further simplify this using some KKT conditions. Okay. This is what we are going to do. Okay. So this is a sort of two-step things that we are going to do. Okay. So now let's look at how do we obtain uh, yeah, dual form of any optimization problem that we are given. Okay. So let's say this is your primal problem. This I have taken directly from the lecture. So the problem is something like minimize f of x. So we also had something like minimize half of this norm w. Okay, you can take square also. Okay, and subject to some constraint gix is less than equal to 0. The same thing we had. So we had something like yi w transpose x minus b is greater than equal to 0. So we can just multiply it by minus to get less than equal to 0. Okay. Then uh, how is Lagrangian given for this problem P? So we take f of x, that is the function that we want to minimize, and for every constraint that we have, we associate it with the Lagrange multiplier and we take their sum. Okay. So f of x plus lambda 1 times gix plus lambda 2 times g2x and so on. Okay. So this is the Lagrange function. Then the dual problem is given by maximize Lagrange function. Okay, so we obtain this Lagrange function subject to the constraint that the gradient of your Lagrange function with respect to x is equal to 0, and your Lagrange constraints that you get, Lagrange coefficient, that is greater than equal to 0. Okay, so this is just the simplified form of the above. So this is f of x plus this is your Lagrange function, and then the gradient is gradient of f again with respect to x plus the gradient of this thing, because this is summation, the thing splits up, and this is what you obtain. Okay. Now, if your SVM problem is given as minimize, this is problem P1, okay, half W transpose W subject to yeah. So this is written in this form. Your yi is now replaced by di, right? W transpose xi minus b is greater than equal to 1. Okay. Yes. So now you can just convert it to the standard form. Okay. And we want this thing to be less than equal to 0. So you take this term on this side, then we obtain 1 minus di w transpose xi minus b is less than equal to 0. Okay. So if we write its Lagrangian, we get f of x plus alpha is your Lagrange multiplier, and these are your coefficients, these are your GI of x. Okay. Then its dual problem is given by maximize this quantity, right? Maximize L of W of P of alpha subject to its gradient with respect to W being 0. Okay. And now you have one more, because the coefficients that you were maximizing or minimizing with respect to was not only your W but also B. So for example, if you have f of x, then you want to, this is a function of x, right? Over here, your this minimization or maximization thing was a function of W and B. So these are the constraints that you need to find in order to maximize or minimize. Okay. So that's why we also have a term which is its derivative with respect to B is equal to 0. Okay. So this will come back to in a while, the last statement, whatever is written. So till now, you just remember that we have reached to the dual. So what I said, we have some primal. We'll get the dual out of it. Then we'll use some KKT condition to reduce it into simpler form. Okay. Okay. So now I think you might have forgot, some of you might remember also what is KKT conditions. So this is from portion from last lecture. So if you have a constraint optimization problem, that is something like minimize f of x subject to gi of x is less than equal to 0, then a local optimal point must satisfy following condition. Okay, this is just your Lagrangian. Okay, that is gradient of your Lagrangian. This must be equal to 0, and this is what we proposed when writing our constraint. So we don't get any extra information from here, right? This is just gi of x is less than equal to 0. This is already a constraint, no extra information. The third one, that is your complementary slackness condition. Here you have some extra conditions, that your Lagrange multiplier times the constraint must be equal to 0. Okay, so we'll use this particular thing. Fourth one is also trivial. Okay, so the problem again was minimize half W transpose W. Okay, subject to the constraints that we got was 1 minus di and then W transpose x minus b is 0. Okay. Now, what are the KKT conditions? That the Lagrange must be 0. With respect to b, it must be 0. This is just your constraints. Now, fifth condition says that your alpha I times these constraints must be equal to 0. Okay. Now, let's get to what was written over here. So, it says that if we use KKT condition 2 and 3, we get some values for W and we get some extra condition. Okay. So, here is KKT condition 2 and 3. Okay. So, let's look at the Lagrange that we got. Okay. So, now if you take its derivative with respect to W, you will get half W plus this term goes to 0. This is summation I is equal to 1 to m, and then you will get minus alpha I di xi. Okay, and this is equal to 0, right? Yeah, yes, this will be equal to 0. So this is W transpose W, so this is 2W. So you'll get 2 by 2 over here, you'll get only W here because this is norm of W square, so you'll get something like 2. So this would be nothing but W1 square plus W2 square, right? So you at every position you'll get 2W1, 2W2. So you'll have 2W when you take the gradient, okay? So this would mean that my W is nothing but alpha I di xi, okay? I is equal to 1 to m, okay? And if you just take its derivative with respect to b, then you get an extra condition that your summation over 1 to m alpha I di is nothing but 0, okay? So they have just put this thing over here. In place of w, they have placed what we had, that alpha I di xi, okay? So you get summation over two variables. But now, because when you take, let's say this is W1, W2, W3, okay, this is W1, W2, W3. So first W1 gets multiplied by W1. So that would induce alpha 1, alpha 2, D1, D2, X1, X2, right? So, yeah, so it will be alpha, alpha 1, D1, D1, right? Everything 1 when you multiply W1 by W1. Then you take its sum when W1 is multiplied by W2. That's why we have index running in both these variables, that is I and j. So we had W is equal to alpha I di, right? And then we had xi, right? So then we had this summation, okay? So this W transpose W is written in this way, okay? And similarly, we have replaced W over here, and this alpha I di term goes to 0, okay? And so we are just left with this was plus half, and this was minus 1 times the same quantity. That's why you obtained minus half, and this term is left over here. So this is the Lagrangian that we get at the end, okay? So this is your I is equal to m alpha I minus 1 by 2 summation I is equal to 1 to m summation j is equal to 1 to m alpha I alpha j dj di xi transpose xj. So just a recall that when we reduced our primal to dual, we wanted to maximize this thing, that is our Lagrangian, subject to these constraints, okay? Now we have formed a another form of our L. So that's why what we want to do is we want to maximize this now subject to these constraints, okay? So what I wanted to see you is that this can be solved by some solver, that is fine, okay? What you need to see is that we have dot product of xi with xj in the like this objective function, okay? So this is how we obtain the dual form of whatever you want to maximize or minimize, okay? So any doubt in this, then we will move to this kernel thing. I want to just motivate it from here, okay? So
Sir, one
yes,
minute, sir.
yes,
Can you go
yes,
on the
sure,
corner
sure.
moment? Slowly, yeah, yeah. 1 minute. Just I want to know that you're doing, the W equal to alpha I dixi,
Yeah.
I think this is you bought from some equation, no? I think
Yeah,
from where you made that.
that was from the KKT condition, this particular condition.
Uh, okay, so 1 minus d0. No, how you written that W is equal to alpha e, no, that how you from, I think you derived it, I got it
Huh.
actually, but just here, here,
Here,
here.
here.
Okay, okay.
Yeah.
From, yeah, W plus, this is what our that Lagrange only. Basically,
Hmm.
W plus is nothing but from the Lagrange. From that
Right.
again, you derive W equal to sigma whatever, and that you're
Hmm.
again replacing the, or again you're replacing that same thing in the Laplace, that Lagrange, so that will minimize with the all, we can express the alpha and di.
Huh.
And
Exactly.
why you're taking di? Actually, it's like yi only, am I right? It's data
Huh.
because.
Di is the yi that professor has used in his notation. This is yi. Yeah.
Yeah. Okay, in general, Lagrange they may use some di distance, something like that. That's why it is replaced with the yi actually.
Huh.
In
This
general,
would,
there is, yeah.
yeah, this would be the label of your data. Di would be the label of your data.
Okay, okay. That's what I didn't understood the di. Now you're telling
Hmm.
I am able to correlate. Okay, understood. Thank you.
Okay. Okay. Now, so we just talked about linear classifiers till now. So whenever I said about SVM, what I said is we will try to find some line that will separate. But a general trick that works not only in SVM but in all of machine learning is something that is known as lifting of planes, or you can say you want to change your features to nonlinear features. So in real life, the kind of data sets that you get are generally not linear. Okay, let's say you have something like this. Okay, these are all your red points. Okay, and these are your green points. Okay, you can see that there is a clear curve that can separate these two type of data sets, but this curve is not a linear, right? Okay. So what I think we talked about it also when we were doing logistic regression. What we can do is to introduce non-linearity. We add some features or we modify these features. Okay, so let's say you have some features x1, x2. If you include, let's say, x1 square, and the next time you include x1, x2, let's say you even include x3, x2 square. Now with these new features, in the new feature space, this separation or the plane that you will be finding, in the new space it will be linear. Okay, so in the lifted space it will be a linear sort of thing. But if you then project that line to your original space, that might not be linear. Okay, for example, let's say this is your two types of plane. If you project your this green part to a height of +1 and you project your red part to the height of -1, then you can easily draw a plane in 2 dimension which can separate these two data points, right? So that's what the idea is to, yeah.
I'm not getting this. Can you please repeat this again?
Okay, so let's take a very simple example. Okay, let's take a one-dimensional line. Okay, so yeah, okay, let's take it. So let's say these are my points. Okay, so is this linearly separable? It is not, right? So I want to move it to a two-dimensional space. Okay, now what I do is I move this green point here, these 3 points here, and this one also here. But for the orange one, I take a better height. Okay, so I lift this to here. Now in the new space, in the R2 space, you can draw a separating hyperplane, right? Okay, this is just an example that I'm giving you. Okay, so even when with respect to the original features, these two data points were not separable. Okay, but we can separate it when we move it to some other space. Okay, one more example I'll give you. I think then it will be more clear. Okay, so let's take two-dimensional data point, cluster of two-dimensional data point. So something like this you have some orange points. Okay, and you have some green points. Okay. Clearly, this is not separable by any line. Although it is separable by this circle, we can draw it, but it is not separable by line. So what if we do that, we define a new feature. Okay, so let's say this is x1, this is x2, right? We have x1 and x2 as two features, and we define a new feature, right? That is the distance of a point from this particular red point, or this yellow red thing that I have drawn in the distance. Then if you just look at the third feature, okay, if you just look at the third feature, if this is your 0, then all your orange points will be close to 0 distances, and all your green points will be far away from this 0 distance. Then you can draw a separating hyperplane. So if you now use x1, x2, and this new thing that we have defined as your features, then in the new space, your data points become linearly separable. Okay. Even if you would have ignored the earlier two, then also it might have become linearly separable. Okay. So what I'm saying is that if you introduce some non-linear features out of your existing features, okay, then you can even classify non-linear you can get non-linear separating hyperplanes. Now am I clear?
यस सर. सर अगर इसी सेम एग्जांपल में अगर हम इसको 3D में प्रोजेक्ट करें, अगर हम जो ऑरेंज वाले पॉइंट्स हैं उनको थोड़ा ऊपर लिफ्ट करें और नीचे वाले नीचे रहने, तो एक प्लेन से भी सेपरेबल हो सकते हैं वो.
हो सकता है, पर अभी हमारे पास जो वो मैंने पहला वाला एग्जांपल के लिए दिया था कि ग्रीन वाले को यहाँ लिफ्ट कर सकते हैं, ऑरेंज वाले को और ऊपर, पर जो भी फीचर हम x3 डिफाइन करेंगे, ठीक है, वो हम एग्जिस्टिंग इंफॉर्मेशन के ऊपर ही कर सकते हैं. ठीक है, तो हम लोगों के पास कोई ना कोई रूल होना चाहिए जिसके बेसिस पे हम लोग किसी भी पॉइंट को बता सकें कि उसको कहाँ पे लिफ्ट करना है. तो अभी अगर हम लोग बोलें कि अंदर वालों को हम नीचे लिफ्ट करते हैं, तो आइडिया वही रहेगा कि हम लोग किसी पॉइंट से उसका डिस्टेंस मेजर करेंगे, ठीक है, और उसके बेसिस पे हम लोग ऊपर या नीचे रखेंगे. ठीक है, देयर शुड बी सम रूल एटलीस्ट, कि अभी जैसे हम लोगों ने x1 और x2 के बेसिस पे, अगर मान लो ये बीच वाला पॉइंट a और b है, तो हम लोग डिस्टेंस ऑफ x1 कॉमा x2 और जो तुम्हारा a कॉमा b है, इसके बेसिस पे तुम कुछ भी डिफाइन कर सकते हो, पर इसको खुद भी एज अ फीचर यूज कर सकते हैं. देयर शुड बी सम रूल दैट शुड बी बेस्ड ऑन एग्जिस्टिंग फीचर्स ओनली. ठीक है.
ठीक है सर.
क्योंकि ऐसे देखने में तो लग रहा है कि हम लोग उसको लिफ्ट कर सकते हैं, बट कौन से पॉइंट को कहाँ पे लिफ्ट करना है, देयर शुड बी सम रूल एसोसिएटेड विद इट. ओके. Okay, so now this is the idea of your kernel function, that for some features you want to lift x to some phi of x. Okay, so some function of x. So for example, your x3 was some function of x1 and x2 and so on, right? But now there is a problem associated with this also. Okay, so if you include one more feature, right, then your computational complexity sort of increases because you have more features. Okay, then if you look at this thing here also, you will have to find one more constraint, because now you will have one more w to find because of one more features. So you will have more alpha is to find. Okay, you will have one more constraint. So with every new feature that you introduce, you have some more these things. Okay, to tackle that, we come up something that is known as kernel function. Okay, so what is the idea or the special quality of a kernel function? So if you remember, in the dual form, we had to calculate this quantity, right? So we want to replace calculating I transpose xj with some phi xi transpose, phi xi transpose phi xj. But what we want is, we don't want to explicitly calculate phi of xi and phi of xj. हम लोगों को अलग से डिस्टेंस नहीं निकालना है. We don't want this distance to be calculated explicitly. What we want is that if this dot product is some function of xa and xb itself, okay, then those kind of functions are known as kernel functions. Okay. So instead of this xi transpose xj in your maximization, we replace this by kernel of xa and xj, and then we sort of maximize or minimize this thing to obtain our hyperplane, and the hyperplane that we'll obtain is non-linear. Okay, so here are some common or the useful kernel functions that you can use in your example or your problems. So first one is known as, first I'll introduce a simple one, that is your linear kernel. Okay, so linear kernel is nothing. It's, if you have a kernel between xa and xb, it's same as x1 dot xb. Okay, this does not make any difference. Second one is known as polynomial kernel. It is given by, is nothing but 1 plus xa transpose xp, and then to the power p. This power p is, so you can vary it and you will get new kernels. Okay. Third kernel that we have is known as Gaussian kernel. So this would look very similar to your normal distribution that you did in last class. So this is E minus norm of xa minus xp. So you'll replace your dot product with these things. Okay, 2 sigma square. Okay, and we also have something known as sigmoid, in which we have tan h beta naught times xa dot xb plus some beta 1, and you take tan h outside this. So these are some common kernel functions that one can use. How to use, I think that has been elaborately done in the last 2 lectures in the course, not by me, but in the course, where you have Python and SVM. There it has been implemented by sklearn. Okay, so you can try that. Okay, so this is what I had planned for today. So if anybody has any doubt related to today's lecture, you can ask. After that, we'll try to solve whatever Abhinav has to ask. Anybody has anything to ask about today's lecture can ask. Okay, so one small comment that I want to add is, people nowadays are sort of using very, I would say, not so